विद मैकेनिक्स ऑफ ए सिस्टम ऑफ पार्टिकल्स। पिछले सभी लेक्चर्स के अंदर हमने सिंगल पार्टिकल सिस्टम की बात की है। हमारे मैक्सिमम जो सिस्टम्स हैं, सॉलिड्स हैं, लिक्विड हैं, गैसेस हैं, मैनी पार्टिकल सिस्टम को रिप्रेजेंट करते हैं। तो आज अगर पार्टिकल्स हमारे मोशन में हुए और वो भी बहुत सारे पार्टिकल्स हैं सिस्टम के अंदर, तो उनको हम कैसे डील करेंगे। मिनिमम पार्टिकल्स का नंबर हम 1 मोल से रिप्रेजेंट करते हैं। एवोगैड्रो नंबर ऑफ पार्टिकल हम किसी भी सिस्टम के कंसिडर करते हैं। एवोगैड्रो नंबर ऑफ पार्टिकल्स का मतलब है 10⁻22 पार्टिकल्स को हम रिप्रेजेंट कर रहे हैं। और अगर 10⁻22 पार्टिकल्स है और एक पार्टिकल की मोशन को मैं एक इक्वेशन से रिप्रेजेंट कर रही हूँ, तो मेरे पास सोचिएगा कि एक पार्टिकल के लिए अगर एक इक्वेशन आ रही है तो एक मोल पार्टिकल्स के लिए, क्या ये कहिए एवोगैड्रो नंबर ऑफ पार्टिकल्स के लिए मेरे पास कितनी सारी इक्वेशंस आ जाएंगी। दैट विल बिकम ए कॉम्प्लेक्स सिस्टम. To make this system very easy, we convert this many particle system into single particle system, and due to which we will discuss today the center of mass concept also. Let us start with mechanics of a system of particles. Let us consider we have large number of particles in a system, and we are representing these particles with particle 1 having mass m1, and with respect to any coordinate system, let us consider the position vector of the first particle is r1 moving with velocity v1. Similarly, let us consider this is our second particle representing with position vector r2 having mass m2 moving with velocity v2. And let us consider this is any particle, and this is ith particle having position vector rn, and similarly the velocity of the particle is vn, and let us consider the particle mass is mn, mi, because we have considered the ith particle. So we just denote the uh, position vector with ri, velocity with vi, and mass with mi. Let us consider this is the last particle, nth particle having mass mn, velocity vn, and let us consider the position vector is rm. In this way we can show a system of particles in any coordinate or in any space. We very well know that if there is any ith particle in our system, and if we apply any external force on this ith particle, we will show it with Fi external. This is the external, any push or pull to the given to the ith particle. This external force can increase or decrease the velocity or can change the direction of the motion of the particle. But we very well know that this ith particle have a force of attraction with first particle. The first particle will attract this ith particle in this direction, and let this is represented by F1I, that is the force of on the ith particle due to the first particle. Similarly, the force on the first particle due to the ith particle will attract the first particle in its direction. Then we can represent this force like this, Fi1. It means this is the force on the first particle due to the ith particle. And as force is a vector quantity, we are representing both the forces with a vector. What is the similarity and difference in between the force F1I and Fi1? This is F1I is equal in magnitude with Fi1. It means if the first particle attract the ith particle with 5 Newton of force, with the same force 5 Newton, ith particle will also attract the first particle. What is the difference in between these two forces? The difference is that Fi1 is equal in magnitude with F1I, but they are in opposite direction. If the first force is in this direction, the second force is in this direction. These forces in between the first particle and the ith particle, we are not applying these forces. These are the forces which already present in between the particle. These are the interactions in between the particle, and we can't avoid them. But the characteristic of these forces is that they always happen in pair. They always present in pair. If first particle apply a force on second particle, then the second particle will also apply a force on first particle, and they are equal and opposite forces. And if we sum these type of forces, the internal forces, we get the total sum is equal to 0, as they are equal and opposite, and they always present in pair. And pair, like that, they are present in e- equal and opposite form. If one particle apply a force on second particle, then second particle also apply a force on the first particle. It means there are two type of forces acting on a system of particle. One is known as external force, which we apply from outside, and second is the internal forces which are present in between the particles because of their mutual interaction. And if the particles are charged particle, there may be Coulomb forces also, even though they are present in pair. Hence, there are two type of forces. The first force on the ith particle can be represented like this, that is the external force on the ith particle, and the internal forces on the ith particle can be represented like this, that is gi summation. Internal forces are represented like summation fgi. It means we are representing the force on the first particle, on the ith particle, due to the first particle, the force due to the second particle, the force due to the third particle, and so on. Just missing the term FII, that is the force on the ith particle due to the ith particle, which can't be possible. So the terms summation FGI is representing all these internal forces due to all the particles on the ith particle. According to the second Newton's law of motion, we very well know that there is a relation between force and momentum, and in generalized form, F is equal to dp upon dt. And as we have two type of forces here, one is internal force and another is external, we can represent this case, the relation between force and momentum, for the ith particle. And for the ith particle, we have to represent the force on the ith particle as well as the momentum of the ith particle. As the force on the ith particle, there are two type of forces on the ith particle. One is external force and another is internal force. It means this force is the combination of external force as well as internal force. Hence we can write the force on the ith particle as summation fgi plus fi, that is external force, and this is equal to dpi upon dt. Here the summation is from J is equal to 1 to n, as we have written force due to the first particle on ith particle, second particle apply force on ith particle, third on ith. First, second, third, these terms are representing J, and J is from 1 to n. But there is a condition: J can't be equal to I. Ith particle can't apply any interaction or show any mutual interaction with the ith particle itself. We can explain this whole phenomena with the help of center of mass. Now we will convert all these things into center of mass. If we have to find out the total momentum for the system, then we have to take the total force. This is the case only when we are discussing about the ith particle. But we have to take all the particles of the system, then we have to make summation of this equation, and now the summation is from ith particle 1 to n, because here we are discussing the forces on the only on the ith particle, but there are n number of particles in the system. So if we have to discuss about the whole system, then we have to give a summation to this equation so that we can discuss about the whole system. It means now we can put I is equal to 1, 2, 3 and so on. We will discuss all the forces on the first particle. We will discuss all the forces on the second particle and so on. We all get the total force and total momentum for the system. And uh, in this process we get summation of dpi upon dt. Hence dpi upon dt is the total change in the momentum for the system, and this can be written in the form of mass into velocity. If we are taking the momentum of the ith particle, we can write it mi into vi, that is the mass of the ith particle and velocity of the ith particle. This term is constant with respect to time. The mass remains constant with respect to time, so we can move mi out of the bracket and we will get summation mi dvi upon dt. dvi upon dt, it is the rate of change of the velocity for the ith particle with respect to time period. As we know, according to the definition of the velocity, we can write change of displacement with respect to time period, that will also give the velocity. In terms of position vector change, we can represent the velocity. So the summation dpi upon dt, in the next step we can put vi as dri upon dt. We will get summation mi second order differentiation of ri, and we get this d upon dt vi as substituting as dri upon dt. Now, as mass is a constant quantity, we can move this mass again with ri, and we will get summation second order differentiation of mi ri, or it can also be written as, we can put this operation first and summation second, d square dt square summation mi ri, and this is nothing, this is the total change in the momentum of the system. So we convert the momentum of the particles into the product of their masses and respective position vectors. This term summation mi ri can be written as, or can be known as, first moment of mass of the system. It is also known as first moment of mass of the system. This term, that is the product of summation of the product of mass and the respective position vectors. Here the momentum of change in the momentum for the whole system is represented in the terms of product of mass and the position vector. So we can substitute the value of dpi upon dt from here to this equation, and we will get d square dt square summation mi ri is equal to, this is our momentum, and this is the total force on the system. Can be written, there are two summation with this term, and we can convert these two summation into single like this summation. Here there are two variables I and j, and they are from equal to 1 to n, but the condition is that I is not equal to j, and this first term is representing all the sets, all the pairs of the internal forces plus summation of all the external forces. Let us consider what this term is about. Summation fi external represent the sum of all the external forces. It is representing external force on first particle, external force on second particle, and so on, the external force on the ith particle. If we are adding external force to external force, external force, and external force, what will you get in the end? You will get total external force. So we can replace this summation of external forces with this external force which is applied to the system. Secondly, we will discuss about this summation. This is summation, that is fji, where both I and j are variables from 1 to n, but I is not equal to j. What this term is representing? It is representing force on the first particle due to second particle, first particle due to third particle, first particle due to fourth particle, and so on. Force on the first particle due to the nth particle, and all these forces are the vector sums. It is also representing the forces due to the second particle, and second particle we apply the force on the first particle, it will apply the force on the third particle, but it will not apply the force on the second particle itself, so we are not getting the term F22, and so on. We will get the last term, that is F2n. Similarly, the third particle also apply force on the first, on the second, but it not apply the force on itself, and we will get the total forces like this. And in this way, we will get the force due to the nth particle on first particle, nth particle on second particle, and nth particle on n minus 1. We are not taking the last term fnn because the nth particle is not applying the force on itself. If you are considering what is all these terms are indicating, they are showing the pairs. Here we have fn1, here we have f1n, and we will cancel out each other, and similarly we will cancel each and every force which we are getting in case of internal forces, and in summation total net internal force becomes 0. We can also represent this summation fji, where I and j both are variable, can be written as summation of half fij plus fji. We are dividing fji into two components because fij is also equal to fgi. So we are representing fgi as sum of fgi as well as fij. It means we are getting this force twice here, so we are taking half. And fij plus fgi both are opposite forces. It means this sum is equal to 0. If this sum is equal to 0, it means the total internal force becomes 0. Hence, in our equation for the whole system, this will become the total external force, and this internal force, as it obeys the pair law, it will become 0. And in conclusion, after solving all these factors, we will have the we will left with only two terms, d square dt square, that is the term which we uh, find out when we discuss about the momentum. The momentum becomes like this with summation, which is the reduced equation. And now on the left hand side, as the internal forces becomes zero, only we are left with the external forces. Now this is, we are talking about many particle system. The summation moves from I is equal to 1 to n, and we will get m1 r1 m2 r2 and so on. Even now the problem is very complex one. What we are going to do, we have this whole system of particles. We will move the each particle towards a given point. Let us consider this is the given point. We will put m1 on this point, m2 is also we will take on this point, and similarly we will put all these particles on this point. Now this point where we are taking all the particles, that is known as a center of mass, and the position vector of center of mass can be represented by capital R. What is the center of mass? Center of mass, it is an imaginary point, and its mass is the total sum of all the masses present in the system of particles. But there is a condition. If this whole system is showing some motion, if this whole system is moving with any velocity v, center of mass is also move with velocity v. It means center of mass shows the motion of the whole system, but many particle system is now converted into single particle system. Then how we will find the position vector of center of mass? If the position vector of each particle and the mass of each particle is given. According to the definition, center of mass is an imaginary point where whole mass of the particle body is concentrated or taken, but there is a condition, center of mass represent the body's motion. Even the particles are moved to the center of mass, but even though the center of mass represents the whole motion of the body. Now the position vector of center of mass, that is represented by R, can be calculated with given masses and given position vectors of each particle. This is the mathematical expression for the position vector of center of mass, that is, it is the sum of product of mass with their corresponding position vectors. Mass of the first particle, product with position vector of the first particle. Mass of the second particle, product with the position vector of the second particle, and so all these, add all these terms divided by the masses of each particle, and we will just minimize this expression in the form of summation, that is summation of mi where I moves from 1 to n, and in denominator we will take the total mass as capital M, where capital M is representing the total mass of the body or total mass of the system. Now from our expression what will we get? Summation of mi ri can be written in the terms of total mass and position vector of center of mass. If we will move this term in the left side, we will get m r. What is m? Total mass of the body. And what is r? Position vector of the center of mass. It means the total system is converted into a single particle, and this single particle have mass m, and it is, this particle is known as center of mass, and its position vector from the origin is represented by capital R, and capital R can be given with the help of this formula. Now we will substitute this obtained result in our previous result, that is the relation in between momentum and the external force. What will we get from here? We will get d square upon dt, and instead of summation of MIRI we will put the result in terms of center of mass. We will get M R is equal to external force. As mass is a constant quantity, it will not undergo change with time. We will have m d square r upon dt square, and this is equal to the external force applied. If we differentiate r with respect to time once, what will we get? We will have m d upon dt, and this is v, and v is nothing, it is the velocity of center of mass, because the position vector of center of mass is changing with respect to time. It means if this r is changing with respect to time, then what will change? The position of the center of mass will change. It means this point is moving with velocity VCM, that is the velocity of center of mass, and this happens only when external force is applied on the body. Similarly, if we differentiate it once again, then what will we get? We will get A, that is acceleration of the center of mass, and this is equal to the external force. This is the whole conclusion of our debate, of our discussion. It means when we apply an external force to many particle system, we can consider that many particle system into single particle system, and this applied force will produce an acceleration in the center of mass. We can convert the complex system, many particle system, into a single particle system, but this is single particle represents the same motion as the motion represented by the many particle system when it is going to experience an external force applied on the system. Here the mass can be taken with velocity, and we will get another expression for it also. We will take m with velocity of center of mass, and now this becomes equal to the external force. Mass into velocity, that is momentum, but now we are talking about the mass of the center of mass and velocity of the center of mass. Now the momentum is also of the center of mass. It means p cm divided by dt, and this is equal to external force. It means when we are applying external force to many particle system, and if we are considering it into a single particle, then this applied force will change the momentum of the center of mass itself. This is the concept of center of mass, where we can make our problem very easy. As many particle system has complex equations to study, we can convert the many particle system into single particle system with the help of center of mass. So what is the conclusion? Conclusion is that the many particle system can be easily studied with the help of center of mass, and center of mass, it is an imaginary point where whole mass of the body is supposed to be concentrated, and the whole mass or the center of mass will discuss the motion of the system also.